We'll get started for today. First off, are there any questions on the assignments or what you should be doing for your paper? I'm giving you feedback right now, and hopefully I'll finish that today or tomorrow on your projects. But I want to make sure everyone is setting themselves up for success at the end of the semester. So if you have any questions or things you want to bring up, feel free to unmute yourself, or I'm looking at the chat box as well. If you have anything you want to discuss, now's a good time. All right, I don't hear anything. So we'll get started on the slides for today. We're going to talk a little bit more about metamaterials or architected materials in lecture 11. And you see the slide up here with the title on the top of the slide. And then we'll move on to some interesting 4D printing and then some applications of polymer and composite additive manufacturing. So what we're going to discuss in the next week or so is how are the additive technologies that we've discussed so far, SLA, material jetting, material extrusion AM, different types of polymers, elastomers, SLS, how is all of that materials and process technology used to do really interesting things in the research domain? And then we'll talk about some of the industries and how these industries are thinking about using additive manufacturing of polymers and composites. And so we'll talk less about printing technology per se, although every time we show a paper like this, we can say, okay, this was made using SLA. You know, we can go and look up the polymer that they use. We can look up the printer that they used, or maybe they use material extrusion AM. So we can look up the details in the paper. And so you don't forget or don't ignore the details of printing and materials that are given in the references here. But we're going to talk a little bit more about properties, possibilities, what you can actually do with additive manufacturing of polymers and composites as we move forward here. So any questions? All right. So we left off talking about architected materials where the shape matters, and the shape, or the combination of the shape or the architecting and the combination of the materials properties themselves can give us really interesting bulk properties, or really interesting what we might call effective properties, where as we change the structure of the truss here, these are all made out of the same material, but we can get them to fail differently depending on how the truss is made. And so we looked at just a quick printing example because it was interesting, but some of this type of metamaterial falls under a specific type of metamaterial called an auxetic material. And so let me go back to the YouTube video here to remind you what that is. But usually when you deform a material in one axis, so you squeeze a material in the z-axis, as this is going to show, it spreads out in the x and y. But with the metamaterial approach, what we're going to see in this video is you deform in the z-axis, or you compress in the z-axis, and it actually compresses in the width direction here. I think it doesn't change in the third axis, but this is unusual material behavior, and this is because of the architecting, or because of how the different cells in this material are put together. And this was enabled by 3D printing. So whether we say negative Poisson's ratio, or auxetic material, or architected material, they mean almost the same thing. And so let's just remind ourselves of what that looks like here. Great, so you see the cells deform differently, and as this thing is compressed by a factor of 30 or 40% in the z-axis, it also pulls in 5 or 10% in the other direction. So that's interesting, and that's unusual material behavior, but that's easy to do with these architected or with these metamaterials. Oh, let me make sure PowerPoint comes back here. Maybe we won't be switching between YouTube and PowerPoint. Okay, so as these PowerPoint slides come up, this architecting of the material now incorporates mechanical design and mechanical design strategies in order to make this happen. So as we saw on the YouTube video, these are not just random cells, or this is not a foam that shows this behavior. The cells or the individual unit cells of the material are made in a very, very specific way in order to get this to happen. And there are design rules that we're going to talk about in which these metamaterials can be fabricated from. And then the role of additive manufacturing is that these type of structures were really difficult to make in the past. But of course, with additive, we can make all sorts of great stuff. And so this is just one example here where they talk about three different strategies. So they talk about cut missing ribs, which is just one type of unit cell structure, or 2D reentrant structures or 3D reentrant structures. And you can see that these unit cells have much different things going on in terms of how the struts are aligned and what happens when you start to compress these. We saw in a previous example, and I don't remember exactly where it was. Oh, in this video right here, I don't have a picture of it, but in this video, they printed these elastomer blocks that were flexible in one direction and were stiff when pressed in the other direction. That's a different type of metamaterial, but they all take advantage of these types of design cells. And so you can imagine injection molding something that looks like this, or fabricating something that looks like this by hand is really, really difficult, whereas 3D printing something like this is just like 3D printing anything. You just have to specify the lattice, get your print parameters correct. And then in terms of printing technology, these types of structures are generally accessible with stereolithography, especially if we're at small scale. But you can imagine that this could be made by SLS or even FDM, depending on the length scale that you wanted to use. And of course, we can do elastomers or TPU elastomers in SLS or TPU elastomers in material extrusion AM. And so while a lot of the examples have to deal with stereolithography, we'll see some other examples where different printing technologies are used. And what's cool about some of these materials, and I'll point them out as we go along, some of these materials are anisotropic composites. Other constructions are composites of hard and soft materials. So now you can place different materials in different spots. So you get architecting of a few different types of materials. And in the research domain and in some interesting examples, people have really gone wild with the number of types of materials you can integrate and the types of architectures that you can achieve. So you can fabricate metamaterials that you couldn't, with properties that you couldn't hope to get from a single material. So there's a lot of design philosophy around this and a lot of strategies to make interesting things happen. And so this paper just gives some guidance for at least these types of cellular metamaterials, how these are analyzed, what's happening in the undeformed versus deformed structure. And so there's characteristic curves of how these architected metamaterials work. So, of course, all the stress strains can be analyzed. And what's interesting is that, the stress and strain can be customized to the limits of the material. So whether you're using elastomers or thermoplastics or other types of materials, all these mechanical structures can be analyzed in terms of where is the stress, where is the deformation, and then what's going to happen macroscopically. So if you're interested in design of the architecture, or you're looking for really cool ideas of maybe what should I print to demonstrate the usefulness of my material, rather than printing some standard thing off of Thingiverse, you might be able to think about printing one of these metamaterial structures to show some unique properties. Also, these metamaterials can be used in different ways. And this example right here is showing coloration where, depending on the deformation or depending on the strain, epsilon here, as you strain this material, the color changes. And so you can have a color change with strain that is reversible. So I don't know if everyone out there is familiar with pressure sensitive tape or pressure sensitive film, where you put a piece of film, say, between two components that are going to lay on top of one another, and you can figure out where the pressure points are based on the capsules in the film breaking and showing a different color. This type of metamaterial structure, where you have the unit cells on the inside colored differently than what's behind the unit cells, you can also get a color change depending on the mixing, in this case, of blue and yellow. Those will appear different depending on the strain. And what's nice about a lot of these structures is that they can be reversible. So you get reversible deformation like a spring of these metamaterial structures. And so depending on what functions you embed in the cells, like color change, you can get a self-indicating material. Or now the material is telling you how much it's deformed and potentially where it's deformed by just looking at the color. So you get something that's a mechanical structure plus a sensor. And so that's an interesting approach. I'll pause here if anyone wants to discuss these sort of cellular metamaterials. I just have a couple of examples and then we're going to talk about something else, but I'll pause here if anyone wants to ask a question or bring up a point that they're interested in. Okay, well, feel free to pipe in anytime or put something in the chat. And so this does take some design savvy. I mean, you need some mechanical engineering skills, or at least some CAD skills, to be able to draw something like this to get it 3D printable. But this is also open source knowledge. These papers are out there. There's a big literature on auxetic materials. And some of these strategies you'll see in the next lecture are used for 4D printing. So if you want a structure to deform in a very specific way under stimulus, which is the essence of 4D printing, you need to build the right mechanical structure in order to make that happen. So if you're interested in this, I suggest you check it out. And there's lots of existing knowledge as to how these auxetic type or mechanical metamaterials work. The other really interesting thing that we need to think about with additive manufacturing of polymers and composites is if we're designing structures like the top of a femur here. So this is the part of your upper thigh bone that goes into your hip socket right here. Of course, this is bone. This is going to be a hip socket. The question is, if you need to place an artificial hip in a person, how do you design that structure? Of course, you could make an artificial hip that's completely solid. So you could take a piece of titanium and just make a solid bone replacement, and that's done. Or you could think about the internal structure of bone. So let me make this a little bit more legible. So this bone has an internal structure and it's got different properties in different directions. So just like some of the lattices that we just discussed, bone will have different stress strain properties depending on the direction of the stress and strain. And that seems reasonable, but we want to be able to capture that type of behavior if we go to some sort of artificial construct. And so how do we stiffen bone in the direction that it should be stiff versus how do we infill this material in order to give us anisotropic properties that mimic the real thing? So of course, if you're familiar with 3D printing, you could just take the shape. So here's our artificial shape, and just put a rectangular infill, or you could make it solid, or you could use any pattern you want. But there's a lot of literature coming out now in terms of how to design infills. So this is designed or architected infill to get anisotropic properties. So if you just select 40% infill on your MakerBot, you get a regular grid, and sometimes you have a chance to pick the infill pattern. But the real question is, how do you design the infill to give you the mechanical properties that are appropriate for whatever component you're interested in? So this is one report there, and it's not necessarily making the 3D printed composite porous for blood vessels and everything else. That's not the purpose, but the purpose is, where do you put the reinforcement in order to get the mechanical properties you need? And that can be done using a number of different mathematical routines. And so we won't go into this. This is not a design class, but I wanted to give you some resources as to where you could look for thinking about how this is done. I mean, how does a designer come up with this infill? Is it random? Is it regular? Is it a designed infill? How do you get the CAD software to give you the infill to get the mechanical properties you want? And so this falls under the general branch of topology. Let me write this so everyone can read it. So of course, topology means how things are connected, and topology optimization means we're going to connect all the connections in the right way in order to optimize for whatever mechanical properties we want, or optimize for whatever properties we want. So we can optimize for weight, or we can optimize for strength, or we can optimize for material use, or we can optimize for porosity, or a combination of those. And so this idea of topology optimization is known to a lot of the engineers out there, but with the advent of really powerful CAD software and computing power, and then additive manufacturing that's able to realize structures like this. Topology optimization has been around for a long time, but it's never really been approachable in a way that was pleasing, because it was really hard to manufacture something that looks like this. So you can imagine if you brought that CAD model to a machine shop and said, would you please machine this? That would be a big job. But now with 3D printing, you can do topology optimization, and then you can go print the part that you're interested in. And so this is one really nice example right here from this website. And so this is a metal bracket. And it's designed for strength and designed to be easy to machine. So it looks like your standard metal component. There's lots of things in the world that look exactly like this. And you machine it out of a piece of steel and you're set to go. This bracket right here, which is topology optimized, has same or sufficient strength for the application. And you can see that this is lighter, less material, and it has this organic shape, which turns out works for a lot of the topology optimization. But you can't machine this. And so this has to be made using AM or some other advanced technique. I guess you could cast this thing if you could make a mold that looked like this and demold it, but this generally has to be made using AM. And so what's the cost trade-off compared to the part? Or if this is going to go on an airplane, it might be that the lightness over the life of the part makes a big difference. So even though this topology optimized bracket may be more expensive to start with, because of the fuel savings that the aircraft realizes, by even removing a few ounces over the lifetime might make sense. This is another example right here. And again, you can see these organic shapes. And so if you're interested in looking at some scientific literature, this is a good place to start. And like I said, topology optimization is becoming more and more a part of software packages. And I'm just going to show one example from ANSYS, but this type of goal-oriented analysis and design is starting to become part of how things are designed. So the engineer, based on requirements and based on their experience, can come up with something that looks like this. And then you let the computer take it the rest of the way, because it's really hard for an engineer to sit down and say, oh, my part should look like this versus a triangle bracket that I'm used to designing. So let me switch over to YouTube here and see if this ANSYS video will run. But this will give you some appreciation for, you don't need a whole office of mechanical engineers and designers to come up with something like this. As long as you have robust tools that have been validated and you do your due diligence, these designs are accessible by people that are not necessarily specialists in this field. So let me switch over to YouTube here, because this video is worth looking at. Okay, this is a 14-minute video, but I'm going to skip ahead, and so we're not going to watch all 14 minutes of it, but this gives you some background on how this works.
Dairy farmers go green in many ways. They enhance cows' feed with unused, upcycled plants from other local farms.
All right.
Today we'll be going over some new features with ANSYS version 18 for topology optimization. We'll begin with a simple bracket geometry, apply our boundary conditions and loads, and then finally optimize the part in order to reduce its mass, hence saving material costs should you ever decide to manufacture it. So let's begin. Here I've already opened up ANSYS Workbench version 18.1.
All right, so we'll skip ahead as they get this part ready. Okay, so what they're going to do is they have the part in their mechanical design program, and ANSYS, I think SolidWorks has topology optimization as well as a number of others. And they're going to tell the design software how this bracket is loaded. So where is it stressed and strained? What are the loads? What does that look like? And they're going to use that information of how the part is used in order to do the topology optimization. So you can watch the whole video to see how this is done and what buttons to click. But once they have the first iteration of the part, now they're going to go into the deformation of the part and describe how it's optimized for function.
For physics. Next, we can go ahead and close out of Space Claim. Now that we're outside of Space Claim, we can go ahead and double click on Model, or cell number 4, to open up Mechanical. So once in Mechanical, we can go ahead and we can see our 3D part that we've created here. We can click on Geometry and we can see that we've only imported the solid geometry. And we can go ahead and right-click on Mesh and generate a quick mesh. Now we can see that it's kind of coarse and we want to get the details around where we're going to be applying our boundary conditions. So we can go ahead and click on Sizing, and instead of Adaptive, we'll change it to Proximity and Curvature. We can right-click and then generate Mesh again. Now you can see we have a much finer mesh and we have slightly more details around where we're going to be applying our boundary conditions. So now we're going to go into Static Structural, right-click, and we're going to insert a cylindrical support, and we're going to be choosing the bottom interior face over here, and while holding Control we will select this other face over here, and then we will click on Apply. So now we have two faces selected, and we were going to make the tangential component of this boundary condition free, which means that these joints will be allowed to rotate in this plane. They will not allow to be moved in the Y direction, nor the Z direction or the X direction, radially or axially. Next, we're going to right-click and insert a bearing load, and we're going to put that bearing load at this hole over here, and we'll hit Apply. And instead of using a vector, we will change that to components, and we'll put, let's say, 50 newtons in the X direction and 100 newtons in the Z direction. Now once we have our boundary conditions set, all we need to do is add a solution. So we can go and insert stress and equivalent von Mises stress, and now we're ready to go and solve our solution. So we can either right-click on Solution Solve, or we can hit the Solve button up here. And there you have it. So we can go and click on equivalent stress, and we can see that this is how our part is deforming. And you can click on Graph and click on the play button to get a quick animation of the
Okay, so this is done for every mechanical component that we use. And so what did the engineer design? What does it look like? And then using ANSYS or Abacus or other type of deformation software, how did the component deform? And they make sure that the material that you make this bracket from can deal with the stress and strain that's within the design spec. So this is up to now the usual process of how things are done. But armed with the analysis of the deformation of this typical engineering part, and this is cut out of a piece of sheet stock and then drilled or laser cut or however you want. I mean, thousands of these brackets are made every hour around the world. That's really easy. We know how to do this. But armed with this information of the deformation, now comes the topology optimization. So what routine are you going to use in order to tweak the design for whatever objective you're interested in? So now he's going to talk through this.
Deformation of the bracket. You can see that we have about 83 megapascals, which is under the limit. And as you can see here, that there's a lot of blue, which means that the stress in this area is almost zero. And therefore, we can optimize the mass of this bracket in order to reduce this area and just keep the material that's required. So in order to do this, we're going to close out of mechanical, and we're going to go into our toolbox, and we're going to drag on topology optimization over the solution cell. This will share the information from the analysis that we've just completed and create a topology optimization analysis. Once that's done, we can go ahead and double-click on Setup to launch the mechanical interface with topology optimization. So once in, now you can see that we have the static structural analysis as well as B5, which is the topology optimization branch. So you can see right away that the topology optimizer already excluded the regions of our boundary conditions from the optimization problem, and it chose the full body of the bracket as the design region. So we can go into analysis settings and we can leave this as the default 500 iterations and a convergence accuracy of 0.1. You can also check the output controls and analysis data management for further options. Next, we'll go into optimization region. So as you can see here, the scoping method is all bodies. We only have one body in this case that we want to optimize. And the excluded regions are defined by boundary conditions. So in this case, it excluded these three boundary conditions. Or you can change it from boundary conditions to geometry selection or even name selections. Now for the objective, we're going to leave this as the default. This is the default for static structural. And under response constraint, this is where you can choose exactly what you want to optimize. So in our case, we want to optimize the mass. However, you can also do an optimization for volume, global stress, displacement, local stress, and reaction force. So in our case, we're going to leave it as the default mass, and we're going to change the percent to retain to 60%. Next, we can go into the solution, and we want to make sure that in post-processing, we have export topology STL file, and that's set to yes, because we're going to be exporting this afterwards. So once that's done, all we have to do is click on solution, and we're going to click on solve to optimize. Now once this is running, you can go and click on topology density tracker to track the topology optimization process. Now as it's running, you can also click on solution information, and you can see the convergence curves by changing this to objective mass and response convergence curves. Or you can click on optimization output or solver output, etc. So now we could see that it's done, and we've seen that it removed all of this section over here on the inside of the bracket.
Okay, so that's all of that video that we'll watch, but hopefully that gives you an idea now of what's possible with this type of advanced design software. And so again, we're talking about this in additive manufacturing of polymers and composites, because even though this was a metal example, people are doing the same thing now for optimizing deformation of brackets or optimizing deformation of mechanical structures. This is a paper right here where they were optimizing the design of this truss. And so I'll leave you to read this paper if you'd like to. But as we're able to print structures that couldn't be manufactured previously, we're able to now take advantage of some of these design tools where all of this math has been known for a long time, but it could never be implemented in a way where we could use this for garden variety components like metal brackets or plastic trusses or something like this. So I wanted to make sure to give you some background information on not only what additive processes and additive materials we use in additive manufacturing of polymers and composites, but what's possible when we bring in the design component as well. Any questions on this? Okay, we will switch over to lecture 12. And so if you go to the box and find lecture 12 slides, I can find lecture 12 slides. There they go. Okay, so we're going to talk about 4D printing. And 4D printing is usually described as 3D structures plus time. And so these, in essence, are materials and structures that change in response to stimuli, or in response to a stimulus. Now, this can be mechanical structures that we just talked about. This can be temperature, pH, relative humidity, water, and so it can be all sorts of things, mechanical energy. I think there's a lot of cool 4D printing videos online, and we'll look at a couple. But this is really important when we think about architected materials and we think about the function of materials, because in some applications, we'd really like the material or the component that we're using to do multiple things. And so we don't necessarily have lots of these types of 4D structures today that we use. We generally have components that have consistent properties over a large range of conditions, but this is how people are thinking about designing both new materials. So how do you design a material that responds to a stimulus? And how do you incorporate that material in an architected structure that does something unique? And so we'll go through some examples in this lecture. And if you've ever heard of 4D printing, you know that it's a frontier research area. And so it's worthwhile thinking about the interplay of the structures and materials that make this happen. So this is just one example right here. And let me see if the YouTube is working. We go to this. Oh, there it is. So usually when you add water to a polymer, it expands. So that's very natural in a hydrogel material. You add water, it expands. In this case, this is a metamaterial, but it's an oxidic. And so you're going to pour water on this and you would expect the polymer to expand as it absorbs the water. But the architecture is such that you'll see what happens if this video plays here. So you pour water on it and you see the material shrink based on this oxidic behavior. So this is the opposite of what we would expect based on water absorption and swelling of material. Now, this is a very simple demonstration, and this thing was likely made by hand, but it's an interesting way to think about using deformation and getting a macrostructure to either collapse or expand depending on what you might want.
Wait, can you repeat again why, if it's always supposed to expand, why did it collapse? I didn't understand that part.
Yeah, so just like we saw, let me let the PowerPoint come up here. So just like we saw before in oxidic materials, when you deformed the sample in the Z direction, it drew in the X and Y. Because of the way the unit cells are put together in this material, when you pour water on it, part of the material expands, but that causes the macrostructure to collapse. And so, of course, you can make a lattice that where the material expands when you add water, just like a hydrogel or something like that. But based on the design of the connections between all of the different cells, because of the metamaterial behavior, you can get this construction to shrink while absorbing water rather than expand. So it's sort of the opposite behavior, or it's an oxidic behavior from what the typical material deformation looks like.
Okay, got it. Thanks.
Yeah, and so even today we were talking to people making responsive materials, and they said you always don't need things to expand to deform a material. Sometimes contraction is what you might want a structure to do. And so my advice is don't forget about the different modes of deformation, or talk to your friends that have knowledge in mechanical engineering or mechanics of materials, and you can design in the deformation with this metamaterial approach that you want, depending on the behavior of the material. So you could actually get this structure to expand or contract with the same stimulus, depending on the design of the oxidic, or depending on how these unit cells are collected. So we're going to move on to the canonical example of 4D printing. And so let me go back to YouTube right here, and you'll see how this has been done and how this really came about. If I can find it. How this really came about in terms of 4D printing programmable materials. And so this is from MIT, but this shows some of the behavior and some of the things people are thinking about if this video plays here. Okay, first off, we can see the printing technology. It's in high speed, but this is polyjet printing or material jetting. And so this is printed on a Connex printer and made by Stratasys. And what this is it's a rigid material and a water swellable material. So this is a 3D printed construction that they're going to put in water, and part of it is going to expand and cause this folding that you'll see. So this is printed on a commercial printer, and they just use different inks to get the function that they want. See the UV polymerization, all that stuff about polyjet printing. Sorry for the flashing lights here. It'll be over in a sec. Okay, so they can also do a simulation for this. So if they know the material construction, they can do a deformation simulation in order to get the type of folding or the type of 4D behavior that they want. So they put this flat strand in an aquarium, and when it's sped up 75 times, it folds up. And it only folds up because part of the structure is swelling and part of it is rigid, and so you can get pre-programmed folding. Okay, so this forms into the letters MIT. Of course, we could imagine that says PSU. That's interesting. This is cool because you take a flat structure and you get it to fold up into a three-dimensional structure. So it might be really hard to 3D print that three-dimensional structure to start with, but you can start with something that's flat and then fold it into a three-dimensional object. Okay, this is a self-folding disc, and you'll see how ridged this is, I think, when they take it out. So it's got two types of curvature. It's got the minor curvature in the disc, and then it's got the major curvature. So in all these different structures, it's the same materials, it's the same water swellability, but you can get completely different behavior depending on the architecture or depending on the metamaterial aspects of the design. Okay, and I think this is just a mimic of a protein. That's great, and we've seen this before.
And that is just water, just like plain water, or does it have like different like chemical stuff included in it?
So this is just plain water, but you could envision a scenario where there's different chemicals or different pHs, or it's hot water or cold water. And so the only thing that you need to keep in mind in this area of 4D printing is that you need a material that responds to whatever stimuli you're interested in a predictable way. So you need a material with a known coefficient of thermal expansion, or you need a material that swells to a certain extent that's predictable, because the change in the material properties needs to be predictable so you can predict the shape change. And so the key to designing these things is you need to know how the material is going to respond, and then based on the response of the material, you put that responsive material in specific places to develop your mechanical model for deformation. And so that's described in this paper right here based on the previous video that we saw. And so you really need the material and the geometric program. So you need a material that is responsive to certain stimulus. And then you need a program to design architecture for the desired deformation. And you also need a machine to fabricate. So when you mix all these elements up, the previous demonstration was done in polyjet or material jetting. And so this idea of, so they use a hydrophilic polymer that expands 150% when it encounters water. And so as you build this 3D printed structure with expanding polymer and rigid polymer in a programmed way, you basically program in the deformation that this structure is going to undergo when it encounters, in this case, liquid water. But this hydrophilic polymer that expands 150%, this could be a polymer that changes shape when you change the pH, or it could be a polymer that changes stiffness when you heat it up or cool it down. And so lots of different stimuli can be used, or a polymer that responds to light. So we'll see that in a couple of different examples. But this idea of material response and how to build that material into a metamaterial architecture is really where the 4D printing comes from. And they've made a really nice demonstration of that in this group of work by MIT. Any questions on this so far? Okay, we're going to talk about a couple different modes of 4D printing, and there are actually stimuli responsive materials or smart materials classes on campus. So if you've taken Professor Lauren Zarzar's smart materials class, or Professor Zubeida Uwainis in mechanical engineering also teaches a class on smart structures. So there's various ways to approach this from whatever your discipline is, but this is at the forefront of materials and additive manufacturing research. So I wanted to touch on a couple of different examples and show you what's possible. First off, any questions, any discussion points from class? All right, we'll keep going. Feel free to pipe in. So this is a really cool example from Harvard. So we're still in Boston, or at least Cambridge. So let me bring this YouTube video up. And this is very, very interesting if I can find it. Here we go. And so this is from the WISE Institute. And this institute at Harvard is interested in biologically inspired engineering. And so they're interested in replicating some of the functions and structures of living things. And you'll see that in what they do here. So let me play this video. Okay, so first off, this is direct ink writing. So that's just polymer ink. This, of course, came from Jennifer Lewis's lab. And so they're doing things that we've seen before, but they're writing with this syringe tip using a polymer ink. And the Polymer ink in this case is just, it's got dye in it, so it looks pink, you can see it. But you'll notice that the tool path, or specifically where they lay down the different filaments, really matters in this structure. And so what's interesting about this paper is it's all the same material. So this is not two different materials, it's only one material, but the orientation of the material is different depending on what structure they're interested in. And so you'll see that it's just not to make it look pretty, but the deformation of this material to get the structural change that you want really depends on orientation. And so that's why you have different tool paths in different parts of this component that they're building. Okay, so that flat component is printed and then it's immersed in water. So this is a swellable hydrogel. And depending on the swelling of those different components, you get something that deforms and looks like this. Okay, so there's some other videos on this. And one of the cool things about this paper is that it incorporates a mathematical description of the swelling based on the anisotropy of the material. So this is a hydrogel ink with cellulose nanofibers. And so you can see the nanofibers are aligned in the roads. We would expect that because we have this direct ink writing or material extrusion AM process. And so because the fiber itself is anisotropic, you get different swelling parallel and perpendicular to the fiber. And this different swelling, or this differential swelling, causes mechanical deformation or macroscopic deformation in the structure that's built. And so we see some examples of the real material here. But based on now the transverse and longitudinal swelling of these fibers, you can predict what the strain is for different types of structures that you build, or different densities of these roads. And so that's shown right here. So it's the same hydrogel. So this swells in water and it gets anisotropic swelling of the roads. And then based on the characterization of the anisotropic swelling of the roads, this is just things that you need. Now, if you print a spiral, or if you print this grid, or if you print something that's a mixed structure, you can get different modes of deformation depending on what you're interested in. And what's really interesting about this paper is that the mathematician who developed this swelling model, his name is Mahadevan, and he's an applied mathematician. If you've ever seen the Nova documentary on origami, it's either on PBS streaming, or it might be on Netflix, or it actually might be on YouTube. I'll see if I can send out the link. But he started studying the mathematics of origami, and based on that mathematics, he has applied that same knowledge to how do you take something flat and the roads swell anisotropically, and how do you get it to pop into a three-dimensional shape? And this is a real breakthrough in terms of what's possible with additive manufacturing. Not only additive manufacturing components that change shape, but how might you print something flat and get it to become a three-dimensional object? And so there's lots of cool examples in this paper. And so they talk about different modes of deformation, whether it's twisting or whether it's curling, and how you might design the ligaments in order to mimic a real life orchid, because a real life flower has to assume a three-dimensional shape somehow. And they do that through different types of reinforcement and swelling. So flowers have no way to deform themselves other than through swelling of different components and stiffening of some components versus others. And so they're incorporating this biological mimic where both the material and the structure work together to get whatever macroscopic result they're interested in. So this is another nice example of 4D printing using swelling, but in a little bit different way than we saw before. I think this is the last one right there. Oh yeah, and so they talk about how do you design things with complex curvature in the case of this lily flower. And so depending on the placement of the print path, you can get this thing to have two different types of curvature, which is really interesting. Any questions on this? All right, I think lecture is usually an hour and 15 minutes long, so we still have 15 or 17 minutes to go. So we'll keep going. But this now adds, let's say, another dimension to additive manufacturing of polymers and composites, where now we can get these complex shapes. We not only can make them in our 3D printer, and we know what the materials are, we can now get them to move or respond in whatever way we want. And this is being used today for, say, folding up of antenna in spacecraft, or the solar panels that are on the International Space Station. They weren't sent up as big solar arrays. They were unfolded using origami principles. And so people are very much interested in these sorts of things for advanced technology in folding or concealment or other types of structure, say even self-inflating shelters or self-closing shades. We'll see some responsive structures as we move on here. Okay, but aside from what we saw in the first two examples, there's other modes of responsive materials. So these are shape memory. Polymers. And so this is some examples right here in this article, but this is a special type of construction. So this is known as a stent. And what stents are used for is that they're used to prop open arteries, usually after heart attacks or some damage. And so oftentimes, rather than bypass surgery, if you catch cardiology problems soon enough, you can have a stent placed in your heart. And the stent basically props open the artery and prevents loss of blood flow. And so the stents are put in through a very specific, they're put in through a specific method through another artery. And so they have to be small, but then they need to prop things open. And so you would like to have a stent that starts off as very thin and easy to insert, but you'd like it to pop open when you heat it up. And so body temperature is just a little bit higher than room temperature. And so there's been a lot of these unfolding medical devices, and stents are a key technology here, that you have a temporary shape for the stent made out of a shape memory polymer. You put it in the body, it warms up, and then it pops open. And so even though they do some, Eiffel Tower, that's great, or this spiral using shape memory polymers, and this is also possible with shape memory metals, although they generally don't pop back to their shape at body temperature. But this is another way that you can build in change in shape due to a stimulus. So if you're interested in shape memory polymers or biomedical devices that change shape when they're put in the body, this is something that you could take a look at. So this polymer now is showing a couple different ways that this stimulus can be used in order to integrate two different materials into a final structure. And this actually uses stereolithography, or digital, microstereolithography. And so they're using this DMD. It's usually not digital micro display, it's usually digital micro device. But anyway, now what they're doing is that they're moving their object from material A to material B. So this is two material SLA. We haven't seen many examples of that, and this is a little clunky because they're just changing the material in the vat, but this still shows that it's possible. And so if you're interested in the different polymers they're using, this is what the cross-linking chemistry is. So they can characterize their different composite materials, so they can look at the failure strain and loss modulus as a function of temperature. Of course, they look at things like how much crosslinker is in there and what the modulus is. And so by investigating all these different material properties, they can come up with their 4D design for for how this material construction might look. So you have some basic material characterization you have to do and figure out what the stress strain properties are of these different materials as a function of composition, and in this case, temperature, which they're going to use for their stimulus. And so as they change the temperature, they're getting different strains of this material, or they're getting different shape recoveries. And so they have a programming temperature for the shape responsive polymer. Then they have a recovery temperature. And so depending on what temperature you set the shape, and this is a little bit easier to see, say, in this example, where you have a temporary shape and that's set at a certain temperature. So you program the shape to do one thing, and in this case, it's heated up, it's squeezed together, and then cooled down and frozen. And then when you heat it back up, it has shape memory, so it pops back. And so if you're interested in shape memory polymers, people talk about the programming temperature and the recovery temperature. But now you have different stimuli or different functions that you can use in order to get, in this case, they're showing this multi-material gripper using different materials that they SLA, and they have a heating or a programming and then shape memory type of behavior. And so this isn't necessarily perfectly reversible. You'd like to have this gripper let go at a specific time, but it's difficult and still emerging how you get this round trip shape. So how do you get round trip reversibility versus, in this case, this is just one way reversibility because you have to do the programming mechanically. And so they say, okay, you get a flower to bloom as you increase the temperature. That's probably not as useful as having a mechanical gripper. And so the big question is how to get the gripper to let go So people sometimes will discuss two shape memory temperatures or the hysteresis in shape memory. There aren't very good 3D printing examples of that yet, but this is ongoing research. Oh, there's a question in the chat box. Yes, so they can recompress. So let's go back to the stent example. So once you heat this and you have a printed shape pop open, in order to program it, all you need to do is mechanically compress the sample and then cool it down, and you can freeze it back in its temporary shape. But you have to deform it yourself. It won't automatically, as you change the temperature, it won't automatically open and close, at least in the way that this shape memory polymer is done. So often people talk about different shape memory cycles, or how many shape memory cycles can the material undergo before it fails. And so you can recompress and reprogram the material, but usually you need to input energy in order to make that happen. So you need to compress, or in this case, you would need to open the gripper to heat it and program it again closed for the next cycle. So that's something that people are working on, getting this idea of hysteresis or reversible programming built into the material. Right now, it's just one way. And so you program the flour closed as is at low temperature, and you heat it up and it expands. But you can use this deformation for lots of interesting things. Good question.
Thank you.
Any other questions on this? Okay, well, if you're interested in shape memory polymers, we can talk more about them, but I wanted to show you some examples because this type of structure wouldn't be so easy to make unless we had 3D printing. This is another cool example right here, so I won't play the YouTube video just in case my computer's not up for it. But depending on what you want to do, there's some soft grippers like this. There's some grippers that will say catch fish or gently handle experimental samples. And so you can check this out at the link here. But this all really relies on this idea of a permanent shape versus a temporary shape and how you program that in from a molecular perspective. Now, if you don't have a fancy printer, there's one really interesting article out here from ETH, I think, or a research lab in Zurich. And what they discovered is that PLA is thermally responsive. And so they're folding something that's going to notionally look like this bunny rabbit right here. So this is their origami bunny rabbit. This is their unfolded object. And so if you print this in 2D, and fold up, you'll get back to something that looks like a three-dimensional object from a two-dimensional printed shape. And so that's interesting because I think, well, that's not in this paper, but this can be done using conventional polymers or conventional manufacturing that you might be able to access rather than having polyjet or some other exotic type of printing technology. So this is not as far away from your average capability as you might think. And the reason it folds is that you have thinner and thicker structures. So you have rigid panels and you have joints that will fold up when you, in this case, I think it's warm water stimulus that they use to fold this. And so that's interesting. You can check out that paper if you'd like to take a look at it. Any other questions? Okay, the last thing we'll talk about, and we'll get off of 4D printing, but I wanted to give you a couple different modes of how this might work, is that by deforming objects in different ways and by using this heating and cooling, using this idea of a bimetallic strip or a bimaterial strip, you can get different types of deformation depending on the mechanical properties and depending on the material construction of this laminate. And so here's the reference right here. But what this really relies on is you have a bimaterial assembly. And you know that if, say, in this case, the blue or the blue purple expands more than the yellow, the curvature will be towards the yellow as the blue and purple material expands, and you'll get this bimaterial deformation. And so this works both ways. If you can get the yellow material to shrink and you have a robust interface in this laminate, you'll also get deformation in this direction. So whether you're using expansion or contraction, you can get these types of deformations. And in order to get something complex, say like this bunny to fold up, all you need is deformation in one direction, and you can get this to fold because it folds from flat to curved, and it's all the same type of curvature if you look very closely. What they talked about in the Harvard papers, how do you get the same material construction to fold in complex ways, and they discussed that. But this idea of bimaterial deformation can be used in order to do some really interesting things. So you can characterize the modulus of these materials as a function of time as you heat them up, and you can get an idea of the strain of these different materials as a function of their stress, or the stress strain curves. And these strains are not big, they're only a couple percent. And so if you're straining this bimaterial assembly just a couple percent, you can get big macroscopic deformation in terms of the overall macroscopic change in your material dimensions. So a couple of examples of this is that this is two different materials. One is going to form the sides of the box, and one is going to form where they fold. And in this case, this is reversible. So under cooling, you can get the box to fold up. Under heating, the box will unfold. So now this is a reversible deformation. So unlike the shape memory polymers where you had a programming temperature and you could move one way in the shape memory, now this is a two-way shape memory assembly where you can get this to fold and unfold depending on exactly what you want this to do. And so we can look up, I don't have exactly the materials unless they're listed. Nope, they're not listed here. But we can look up the materials and we can discuss how this deformation is accomplished, but without additive manufacturing tools and without being able to make these complex structures, it'd be very hard to get these sort of active assemblies that people are interested in for advanced applications. So we'll pick up a little bit more on 4D printing next time. We'll talk about magnetic responsive materials and printing with magnetics, because I know that's of particular interest to the class. And if you have any interest in specific 4D printing phenomena or 4D printing examples, please just shoot me an email. I'd be happy to discuss those in class and we can go over some of the details. Any questions? Okay, I think that's our time for today. Again, thanks for bearing with me on the change of time, and I will see you on Zoom on Thursday. Thank you very much.
Thank you.